This example is for MGF 1107, section 14.4, and we are asked to find the minimum cost spanning tree for a graph. And recall that a spanning tree is a tree, which means it's a graph where every edge is a bridge. And it's a spanning tree since there is a path from every vertex to every other vertex in the graph. And we are asked to construct a minimum cost spanning tree, which means we want the total sum of the edges cost or lengths to be a minimum, the lowest. And to do that, we have a process, an algorithm to follow, and it's called Kruskal's algorithm. Kruskal's algorithm is a pretty simple algorithm. What Kruskal's algorithm states is that in your graph, take the edge with the lowest cost first, and then keep taking the next lowest cost edge as long as it doesn't form a circuit. And once you have a spanning tree that is formed, you will have a minimum cost spanning tree. So in this graph, we have 6 cities that are represented here by the vertices with edges or rail systems that connect them, along with the distances in miles from one city to the next as the weight of the edge. Now in this graph, we would first take the edge AB and EC, since they have the lowest weight of 24. So AB would be part of our minimum cost spanning tree, as well as EC, because they both have a weight of 24. The next lowest after that, and they don't form a circuit, so it's fine to take both. The next lowest cost edge is edge AE. It has a weight of 35, and it does not form a circuit, so it's allowable. The next lowest cost edge is 38, yet if we added edge BE, we would have a circuit, ABE, back to A. Thus, we will not select edge BE. After 38, the next lowest cost edge is AD, so we include that in our spanning tree, AD. And we don't quite have a spanning tree yet because we haven't reached a path, or we don't have a path to F. So after 46 would be 55 at the bottom, but if we included edge BC, again we would have a circuit if we had BC. So we do not include edge BC. After 55 is an edge that weighs 56, AF. And you notice if we add edge AF, it does not form a circuit, yet it does form a spanning tree. Thus, what we have left is a minimum cost spanning tree. So if I eliminate the other edges in the graph, I'll have left a spanning tree, which will have a total cost that is the lowest. So again, we wouldn't want edge DC included. We do not want edge FC included, nor DF, nor EF, nor BE, because that would form a circuit even though it had a low cost. That would form a circuit, and so would have BC, even though it had a lower cost than some of the other, a lower weight than some of the other edges. So what we have there is the minimum cost spanning tree. Now the shortest distance that we have would be the sum of the weights of those edges. So we would have 24, 35, another 24, 56, and 46 miles. And if we added those up, we would get 9, 13, 19, 25, 4, 7, 9, 14, 18. 185 miles of track that we would use to connect all those cities. And if it costs $6,900 per mile of railroad track, how much does the commuter rail system cost that we just found? Well, we would go 185 times 6,900, and it'd be a total cost of $1,276,500. So again, what we would do is we would take 6,900 and we times that by every mile of track, which was 185 miles, and we would get $1,276,500. That would be the total cost to construct that minimum cost spanning tree. All other spanning trees for that graph, which relates to those cities, would cost more than that amount.